what we will do today is now like you're gonna see how push relabel and cut matching game kind of combine together now, right? And so what we're gonna do for today is to see how to get this running time, like something like m/5 time algorithm with polylog factor without black box max flow, okay? Such that, and what we're gonna do is just kind of basically find approximate sparse cut. Yeah. So find a 5 sparse cut, or say that, and this is sparse with respect to the degree node weighting. Okay. Or report that the degree node weighting is 5/log² expanding. Okay. So the point is to get something fast without black box. But we will, when we get something fast without black box, we usually just can do it for degree node weighting. Okay. So I hope you recorded, like we will see how to solve this problem using black box max flow once. Okay. But this by itself is not useful for computing expanded decomposition yet. But we will strengthen this algorithm next time. Okay. Today we just see how to solve this one.
Why is it not useful for expander decomposition?
So, like, okay, I mean, you can use it to find just one sparse cut, but you might need to find many sparse cut.
Okay.
For expand, like, I mean, it's useful in the sense that you can use it many times, but if you want nonlinear time expanded decomposition, it's not enough.
Okay.
Yeah. So the one that is enough is the one that, you know, like you find a balanced sparse cut,
Right. Okay.
or say that it's not balanced and then the rest is already expanding. Yeah. Okay. Okay, so we will use push relabel, and let me just keep recalling this thing. Okay. So the setting is that we have a source and sink function in the graph. And what push relabel will do is just to initialize the level of vertices to be 0, initialize the flow to be 0, and we will just kind of maintain some tight edge. And what will happen is that we will keep push or relabel the active node. Okay. So this is what will happen here. Okay. We keep push or relabel active node until like every node, that is every node with access, every node that has access. So this is just the support of the access, right? Until every node with access have level h, maximum h. So this is what it does here. Just find an active node, which is the guy with label less than h with access, and try to push it or relabel it. Okay. So keep doing this, and I just call this box push relabel active guy. Okay. Just kind of, I just shrink it to one line. And I just said that we update F and L using this loop here until every node with access have level h. So that's what it does. And then we just return F and L. Okay. And this push relabel active, this loop here, right? We'll see that we can implement it in mh time total, including the time to maintain the tight edge. It takes mh time in unit capacity graph and mh square in general graph. We can strengthen it, like make it faster using link cut tree data structure. The code, the pseudocode is not exactly like this, but with link cut tree data structure, the point is that even in general graph, once you spend this much time in general graph, you get that all the excess at the end have level h. So that is what the push Relabel is doing. Okay. And we don't really need this today, but just want to recall that what push Relabel kind of always maintain is like the label of vertices never overstretch any edge. Okay. We have that. When you relabel, when you push, it never overstretch any edge. And this is what is needed by the tight edge data structure. And also F is always a preflow. Okay. This is like kind of what we get at all time is kind of, maybe you can say like invariant. Yeah. And at termination, what do we have? We have that all the unsaturated sink is basically not touched. It's never relabeled. It stays at level 0. Okay. This is a guy, the node, who's in the support of in the support of unsaturated sink. It has level 0. And all the excess guy is dead, which means that all the node with excess have level h. Edges are relaxed. So you have this lower bound. Okay. The level lower bound the distance to the unsaturated sink. Okay. Okay. And once you have all this, it just means that at the end, the distance from excess to the unsaturated sink is at least h. Okay. So this is a kind of what push Relabel is doing. Yeah. Okay. Any question about push Relabel? I kind of repeat things, but yeah. Okay. Right. So now, what we're gonna do now is like to use it to do something about sparse cut. Okay. And the problem that we will solve is this sparse cut or match. Okay. I will denote it by cut or match. Okay. And we will use it, and like once we see it, once we can solve this, we will plug it into cut matching game. It's like kind of combined with the thing that we have learned, and we can use it to find sparse cut fast. Okay. But let's see what this subroutine is first. It's defined like this. It's just you have a graph. You can think like capacitated graph even. Okay. And you have a graph. You have A and you have B. And let's say A is smaller than B in degree. And what we want to do is, like given this parameter phi here, and A and B, it's gonna either like find some sparse cut, S that is sparse, phi S, and S is phi sparse. Or otherwise, it's gonna just say that it's gonna send flow from A to B. Okay? Send flow from A to B. That is to match flow from A to B. By how much? basically, like for every node in A, it would send in total, the flow that send in total is like degree U times 5/2. Okay. So just send this much from A to B. You should think like this is basically kind of what we want to do in one round of cut machine game, right? In one round of cut machine game, the cut player chooses A and B, and we need to send flow from A to B, or find sparse cut. We'll see how to plug it into cut machine game later, but this is just the problem definition. Question about the problem definition.
Can we solve this just by using like the flow cut from before? Like
exactly. If you just want, if you are okay with calling MacFlow black box, you literally just basically solve MacFlow by say that just maybe like MacFlow in G and set the source to be just this thing and set the sink to be this thing, degree intersect A and degree G intersect B. And it's gonna either send flow, or if it returns some cut, that's gonna be sparse cut. And the idea why it should be sparse cut is kind of because you see like we just try to send phi like degree. We try to send degree not weighting, but even scale it down by phi, and it got stuck by some cut, so it means that this cut here should be smaller than like degree A here scaled down by phi, so it should be phi sparse. Okay. So this is just the algorithm we learned before. If we use black box MacFlow, but we will not use it. We will not use it now. We're gonna do it ourselves. More questions? Okay, so now we see the algorithm. Okay. The algorithm is just first to set source and sink like usual, like it should be. And now we're gonna try to use push Relabel. So we initialize like the label to be 0, the flow to be empty flow in the beginning. Okay. And now we maintain type H data structure like in push Relabel. On what graph? We do it on residual graph, right? And okay, this is just the H and capacity of residual graph. And we set this weight function to be the normal one, the R1 weight function. So every edge has like length 1. Okay. Now, important point is that we set H to be something small. Previously, we see how to compute MacFlow when we set H to be like n plus 1. Right? And but here it's like if you think of phi as quite something like, let's say 1/log, then this is just polylog. So this is kind of small. Okay. This like at the end the running time is mh, and basically if this is basically small when h is small. Okay, and what we do next is just to push a relabel the active node until every node with access is dead, like before. just update F and L until every access is dead. Okay. Now, what's next is just to check if there is any excess. Like, suppose that once we are done with this, there are two cases, whether there is excess remaining or not. If not, then I just say I return the flow. Okay. And I claim that it's gonna be this case. I successfully send out the flow. But otherwise, we're gonna try to find a sparse cut. There is some excess here. So what we're gonna do, we're gonna define the graph. Let me define what this is by layer. Basically, you start with level 0 up to h, up to level h, right? And basically, there is a level 0 node. This contains the unsaturated sink, and then level 1, level 2, level 3, and so on. So Li is just all the node with level I. And it can define this thing in a natural way, like L at least I. So L at least 3. L at least 3 is this thing. Okay. L less than 3 is this thing. Okay. And next, so this is now an algorithm on how to find a sparse cut, right? So define this first. This is not just definition. And now I'm just gonna let G consecutive to be the graph that only contain edges between consecutive layer. It's just a subgraph that only contains edges that connects between consecutive layer. It doesn't all these edges don't skip layer. Okay. So we're gonna have G-con. Maybe I draw it. G-con is such that it has layer, and all edges are only between layer. It's a layer graph. Okay. L0, L1, L2, L3. Okay. LH. And what we're going to do next is to find one layer I, such that when you look at G-con, right? I'm now looking at G-con. I want that basically this cut is sparse in G-con. It's phi sparse in G-con. Okay, so I want to find a cut. I want to find I. Okay, maybe this is Li. I want to find I such that this cut, this L at least I. When you look at G-con, okay, just look at all edges, all capacitated edge across this cut. Right, is phi over 2 sparse in G-con. Okay, so this is just smaller than the degree on both sides times phi. And then I just return this. Okay. So I really just look at G-con and find a phi sparse cut in G-con and claim that this actually is a phi sparse cut in the real graph. Okay. Is the algorithm clear? Yeah.
Okay, so one can, I guess, but there could be more edges, and then they'll be cut out.
Definitely.
That's the next step.
Like it's not clear why this is correct. There could totally be edges crossing like that skip layer. But we want to say that there cannot be too many of them. Okay. So first, can you tell me like maybe like in this case first, why this looks like a correct answer? So this is the case when we just say that we claim that there is no excess. So we claim that F basically must have sent all the source, like it saturate the source and respect the sink. Why do you think this should be correct? Yeah.
It's kind of just by definition because like there's no more excess, so it saturates it. So it's
Exactly. It's kind of by kind of definition. F is always a pre-flow. It's basically a flow with some excess. And we try to send flow from this source to this sink. But once there is no excess left, it just means that we successfully saturate all this flow from the source. And like we respect the sink. Okay. So in this case, it's kind of almost nothing, like not much to prove. Like we are done. Okay. So it's just why this should be correct. Okay. Let's see the running time for a bit. Okay. So like there are basically kind of two non-trivial part. One is like this part. Okay. Just to basically do the push Relabel like before. Okay. And another part is the sweep cut part. Okay. To compute G consecutive is just linear time, right? We have the label, just construct G con in linear time. But sweep cut, I claim that we can compute this, we can find this I in linear time too. How would you think, how would we do it? Okay. So like we have G con, and if we trivially just look at each I and like check what if the cut size and compare with this thing, each of this comparison like might take linear time, and you go to the next one, you might spend another linear time. Okay. How would you do everything in total linear time?
I mean, like as you sort of move through the layers, you can keep track of like which layers each edge that you've already sort of like entered
Yeah.
is like going to, right? And then only remove it after you've like gone past that level.
Yeah, you basically keep track of the degree, like, and you yeah, like you said, you kind of sweep through this thing. Go to the first layer, you can compute this one. You update what you like. You kind of update this cut. Go to the next one. Like every time that you like move vertices from one node to inside the cut, that spend time like degree of that node. But basically each node you spend degree time in total because you just sweep in one go. So you spend time just the sum of degree of nodes. So that's just linear time. Sweep cut is linear time. So the only thing that like is kind of non-trivial, like not linear time, is still like the push Relabel step. Okay. Just the same push Relabel. Okay. So this is dominated by the just trying to push a relabel the active node. And let's say for now, I just use the link cut tree one. So that takes mh log n. Okay. H is something like log degree over phi. Log degree over phi. And let's say degree is like something like poly n. Maybe the graph is capacitated, but let's say it's poly n. So it's log n too. This is basically m log square over phi. So it's still fast. Okay. So why do I use link cut tree? Because you see like what, like this graph here, okay. The reason I use link cut tree is because the graph itself is capacitated. But suppose that the graph has unit capacity. Suppose that this graph has unit capacity. This is like unit capacity. Okay. As it is right now, it's not too clear that you can just use basic push relabel. And the reason is that the source and sink here is not integral. Okay. Like when I present that basic push relabel algorithm takes mh time, that's when like the graph has unit capacity and source sink are integral. Okay. Here the source and sink are not integral. It's kind of scaled down by like a phi. Okay. But what you could do is, for example, scale everything up by phi. So make this integral. And for each edge of the graph, it become like maybe parallel edges of 1 over phi. So that would work. But then the running time, mh here would be, now it's going to be m over phi. You see, like because we scale up. So that would be like m over phi square. So not so great. But it's okay, but it's not so great. If we just use basic push relabel like without care. But I want to note quickly that actually, if the graph has unit capacity, you can really just pay mh actually. Okay. And you get this better running time. This is not immediate, as I said, because source and sink are not integral. But I will not talk about this for now. Like it just takes more careful analysis of basic push relabel. So that I can skip this thing, I just use link cut tree to forget about all these details, and we pay 1 more log n. Okay, but this is just running time. The main thing is now just here. Why this is a sparse cut? Okay. Why a sparse cut in gcon is a sparse cut in the whole graph? That's the question. Okay. And let's analyze it. Okay. In the case when it's matched, we are done. Okay. Let's analyze the case when sparse cut case. So what I do first is like I gonna first prove that the algorithm is even well defined. meaning that actually there is a sparse cut in gcon. Okay. And we will use important like this ball growing argument, which is maybe you have seen it. If you haven't seen it, then it's really useful. Yeah. So what we're gonna prove is this, right? There exists some layer k such that this cut on gcon is phi sparse. Oh, actually I want 4 here, so this should be 4. Okay. Okay. There exists a sparse cut in gcon. Okay. So, okay. Let's draw it. You have level 0 and level h. Okay. And let me assume for now that like this level, like that this side is smaller than this side. Like this side, like it's a bit smaller than this. Okay. This is smaller than the half. If not, then like if this is the case, then we're gonna grow ball from this side. But if like this is not the case, we're gonna just grow ball from this side. So okay, it's just like basic assumption I'm gonna assume for now. Okay. So.
Wait, sorry, what's gcon again?
Oh, gcon? Gcon is G, but it only contains edges that don't skip layer.
Okay.
So it only contains edges that don't skip layer, like this, consecutive. Okay. Okay. So now the claim is that there are gonna be some layer k, okay, layer k, such that the cut here is smaller than the degree of the cut, the degree of like the cuts. Yeah, the cut size is smaller than the volume, basically, by phi. Okay. And because we assume that this side, this half, this like on this half is smaller than half, then it means that this is also smaller than the complement too. Okay. And we would be done if we can show this. Okay. Okay. So why this should exist? Suppose that like we're gonna kind of look at like first layer h and then layer h minus 1, minus 2. Let's look at this layer first. Okay. Layer h. Suppose that this is not true. Suppose that the cut is not sparse. Then what we get that maybe I should draw it like this. Maybe let me draw it like this. L0, LH. Okay. Suppose that this is not true. Suppose that this is big, right? What we get is like if you look at this cut, the layer like this h minus 1, at least h minus 1. This is what is going to be at least the degree, the volume of this part plus the edge crossing the cut, right? And note that this edge crossing the cut, it never go out, it never skip layer. It just go to this layer h-1 because this is in G-con. Okay. So this is just true, you see, in G-con. Okay. But if this is the case, if the claim doesn't hold for k equal h, then it means that the cut here is quite big. It's like at least 5 fraction. So it means that the volume of the cut, the layer from h-1 compared to the layer h, it grows by at least like 1 plus 5/4 factor. Just because this is at least 5/4 of this one. So if the cut is not sparse, when you grow it by 1 step, then the volume grow by this factor. Okay. This might be small, but you know that you can continue this. And this kind of grow exponentially, right? So how many layers can you expect that this can happen? Just log n. Log n is not enough.
Log something n.
Yeah, it's like it should be
Over log of.
So P or something.
yeah log of this thing.
Yeah.
No,
Please.
So P log n.
right. So that is like log n over phi. Yeah. Okay, that's basically like if it grows by this factor many times, then it's just going to be too big basically. Okay. So I can be formal. Suppose that it doesn't hold for when the layer like from layer h-1 up to like h/2. Okay. So it just means that like it means that when you grow this thing, it keep bigger and keep getting bigger up to like you grow this for h/2 times and it keep getting bigger. And this one, the volume of layer at least h/2 is going to be this factor to the like power h/2 times this. Okay. But yeah, h is like this one. Okay. So the way you think about this is just 1 plus phi is basically e to the phi over 4, right? And if you multiply by h over, and if this is like to the h, then this is e phi. And this is like log of degree over phi times degree times phi, something. Okay. The point is like multiply by 100 here. So this would be at least something like degree g over phi to the 100 or something like that. How big is this? Can you know about this one? Well, it's at least 1. Nothing. It's yeah. I don't know. Actually, why do I need phi here? I don't need it. Yeah. So this is just 100 to the degree to the 10. So this is at least degree to the 10. So that's contradiction. Okay. Okay. So are we agree that there must exist this K such that like it's sparse? And yeah, we assumed before that we grow like this is like a smaller side. So if it's sparse with respect to the volume here, it's gonna sparse with respect to volume here too. So we are done with this. Okay. There indeed exists some cut in G-con that is sparse. And again, the idea is like as long as when you have a graph such that the edges are only between consecutive layer, you can reason about like ball growing layer by layer, and you don't overcount thing. Okay. So ball growing usually just work when you have like this consecutive layer of edges. Okay. Okay. So now in G-con there is a sparse cut. So now let's say we fix this cut. Okay. We're gonna now show that this cut is also sparse in the graph, original graph. So what we need to bound is to bound the size of the cut in G, not in G-con. And now I claim this. The cut size in G is basically G-con twice, at most G-con twice of G-con plus the flow out of the cut. This we see before that this is small. We're gonna have proof that this is small later, but let's see why this is true first. So what I'm gonna prove is this actually. Maybe interpret it like this. We're gonna analyze net flow out of the cut. Okay. And I say that this net flow is gonna be at least cut size, but it can be reduced by this much. So why this is the case? Maybe imagine this first. Okay. I draw it. This is L at least K. And this is L K minus 1. And LK at most K minus 2. Okay. Suppose that all cut edges skip level first. Suppose that actually in G-con is actually empty. Okay. So suppose that all the cut edges really skip level like this. Okay. In this case, if this is the case, then I claim that flow out of this is actually saturated. So it's exactly the cut size. Any idea why this should be the case?
Like if it weren't saturated, then like you would sort of explore it in like the push relabel algorithm, right? And it like would be on a different layer.
Yeah, exactly. Like, so the idea is that these are edges that skip layer. Okay. And if you look at the residual graph, okay, what do we know about edges in residual graph? There's no overstretched edge because we maintain tight edge data structure on top of residual graph. Okay. But if you look at this edge, and actually this edge in residual graph, it goes in this direction. That would be overstretched, right? Because every edge has length 1, but now it's skip level. So it means that in the residual graph, in like this edge UV, in residual graph, it actually must look like this. There's no like downhill edge, only uphill edge in residual graph. But every edge that skip level must looks like this in residual graph, no downhill. But if it only go uphill like this, it means what? It means that the flow is just saturated on all of these edges. So that like all the flow F actually saturated all these screen edges. So F out of the cut just saturated all edges. So are you convinced that like without skip, like if our edges are skipping levels, we have this. Okay. Okay. But now maybe some edges are not skipping level. These are edges exactly the one from GCon, right? Something like may not skip level. Some edges that cross the cut do not skip level. The guys that don't skip level have total capacity, just the cut size in GCon. So if this guy that don't skip level don't have any flow on it, then it would reduce the flow out, the net flow out, by this much. But actually, on these red edges, the edges on GCon, the flow might even go in, right? So if the flow go in, then how much would it reduce the net flow out? It will reduce it by twice of its capacity. Okay, so the flow might even send, like F might even send flow into this cut. So this might contribute like minus of the total capacity of edges in GCon, the cut edges in GCon. Okay. So that's why you get like, if there is no GCon edges, you have this, but with GCon edges, you might reduce it by twice its capacity. Reduce the net flow out by twice the capacity. Okay, so we have this one, which means that we get this. Questions? Okay, so now it's just about bounding this one. We know this is small, right? This is kind of at most this is like at most 5 times the degree on both sides. So yeah, just need to bound this one. Okay. How much is its flow out? So, well, this is quite simple. I claim that flow out of this cut is at most the source inside it minus the sink capacity in it. Okay. This is quite intuitive, really intuitive actually. Because, okay, you have level 0, level h, and let's say we look at the cut here, and we want to analyze flow out of the cut. Okay. So we want to see like how much net flow out of F, out of this cut is. Now, the total unit of mass that originate inside the cut is just the source in it. Okay? So it can send flow, net flow out of it is at most this for sure. But we know that out of this mass that originate inside, this many units must be absorbed inside the cut first, right? Why this many units must be absorbed inside? Because you see, like, if this node has sink capacity 5, I claim that if the node U is here, then like there must be flow, 5 units of flow absorbed at U already. It cannot be like unsaturated. Why is that? Because if this sink is unsaturated, where should it be?
0.
0. Right? Everything, yeah. Only unsaturated thing is here. Everything else beyond this, they are all saturated. So everything, like the sink capacity here, they are saturated. So the source, you have this much mass, it must be absorbed by this. So the net flow out of it is just the initial mass minus the sink. Okay. Good. So I hope you're convinced of this. So now I just need to analyze this one. Okay. Now we want to say that this actually now, like, it's the last step now. We want to say that this is like phi over 2, like this degree of this thing, just the usual thing. Degree L less than K. Okay. We want to prove this. Can you prove just one direction? Let's say, can you prove this? Why this should be at most why it should be the case? So yeah, why this should be the case? How big is this? First recall how do we define the source? We define the source to be degree restricted to A. So how big is this thing?
Like phi over 2 times degree of G intersect the nodes in L greater than or equal to K.
Phi over 2 times degree of what again?
Of like L greater than or equal to k.
Right. Just this? It's not quite this. Intersect A.
Yes.
Exactly. Intersect A. Really just, yeah, almost by definition, you get this much for every node inside A. So this is the case. But then this is just obviously at most degree G of L at least K without restriction to A. Okay. So this is clear. Yeah. Okay. It's also quite clear on the other side too. Just need more calculation. Okay. So, actually, it's going to be the case that for every S, this source of S minus sink of S is at most this one. Okay. And one direction is easy, like we just did. Even source of S is at most this much, which is at most degree of S times the. So this part is done. How about this part? Well, it just do it from another side, which you can have a look. But I just gonna say that I can just go through it quickly, but it's not too illuminating. We basically, I want to say that this whole thing, okay, this whole thing is at most this much. The sink from other side. Why is that the case? Here is because this thing is just if it's true if and only if this is the case. It's at most the total sink. Because I just move it to this side. But we have that A is smaller than B. This is why I need A is smaller than B. So even the total source is smaller than the total sink. So this part is smaller than the total sink. Okay. So we have this bound is at most this. And now we can bound this thing like before. This thing, total sink outside S is at most degree of B minus S, scaled down by phi. Okay. So just the sink capacity restricted to B, which is at most B is at most the whole graph. So we are done. Okay. So what do we have now? We get everything. We get that the same cut when you look at G is at most twice times the cut size in Gcon plus this. This part is even sparse in Gcon, which is a subgraph of G. Okay. And this part, we just show that is at most, this should be, L at least K, L less than K. This part is at most this by what we just proved. Okay. So this is phi over 4 times 2 plus phi over 2. So that's phi. So we're done. Okay. So to conclude, right? We just solve cut or mesh problem. We either find a sparse cut or we mesh. Mesh the whole thing or find some sparse cut. And what we do is just run push Relabel up to something like log over phi level. And if you don't have excess, you're done. If there is excess, you can do some sweep cut, fire some layer that is sparse. And okay. So once we have this, let's see how we plug it, like why we can solve this problem that we have seen before, which is like a sparse cut or expand, right? So we have the graph and the phi, and we either want to find a phi sparse cut with respect to degree, or now just say that the degree node weighting is expanding. Okay. And the algorithm will take this time, and it can be improved to 3 if we don't use link cut tree. We learned how to solve this before using cut matching game, where the running time is the time for the cut player, and we call max flow this many times. Now we're just gonna replace max flow call with the thing that we just learned. We're just gonna replace max flow call with this algorithm, the sparse cut or mesh. So all we need to do is just to verify that like sparse cut or mesh it's a valid cut, it's a valid matching player. Okay. Good. So yeah, when phi is quite large, this is actually faster than like calling max flow. Yeah. And there is no black box now. Okay, so let's see. Good. Yeah, let's just go through this. I'm just gonna recall quickly, right? The algorithm to solve this problem, even when you use black box max flow, is like it's gonna be very similar to black box max flow. We just replace black box max flow with our cut or mesh. So we start with like empty graph for the cut player, and we just have log square round for cut matching game, right? In each round, the cut player gonna choose some A and B. Yeah. And previously, what we do is we're just gonna call max flow from A to B with appropriate sort and sink. Basically, this sort and sink. We just call max flow from A to B with this sort and sink. But now we just do the same thing, but we just use our own push relabel, call it cut or mesh. If it gives you a cut, we saw before that it's a sparse cut, so we're done. If it gives you a flow, it basically meshes all the A side to the B side. So it saturated all the guys in A and respect all the guys in B. And in cut matching game, right? Like all you need from the matching player is just it gives you some arbitrary matching that match all the guy on the smaller side on the A side. This just do exactly what we need to do. So that's the valid matching. And we add this matching to graph for the cut player and continue. And once we complete log square rounds, then we can say that this node weighting here is expanding. I will not prove this, it's kind of the same proof. Okay. And yeah, the running time, this is the run time for cut player. Run time for matching player is this one. Because you have R round, and in each round you use cut or mesh. That takes this much. You can improve it to 3, but yeah. Okay. So I hope that, like, yeah, any question about this? Yeah.
Sorry, does the improvement to like log cubed, where does the improvement, like which half does it come in? Is it like the The cut or expand part, or is it like the cut or like sparse cut?
Oh,
part?
the improvement come from this one.
Okay.
This used to be, we used to just call MacFlow,
Right. Okay. Yes. I see.
and we just don't call MacFlow. Yeah. Right. So this used to be TM.
Gotcha. Yes.
Okay. Okay, good. So questions? Okay. So we this is like basically this is a kind of the first application of cut matching game, and we now like don't use black box MacFlow. We just build our own algorithm. Okay. But if you recall, like to get fast expanded decomposition, this version is not enough. We want to find like balanced sparse cut or get expanding set, large expanding set. Okay. So, and the subroutine that we want, like the thing that is kind of to get balanced sparse cut or giant expanding set, we need some subroutine similar to cut or mesh. But it needs to be stronger. Okay, that is going to be this thing. Cut and mesh outside the cut. Okay, so let's see what it is. So not just cut or mesh, it's cut and mesh. And also mesh outside the cut. We're going to solve this in next class, though. But let's see why it's enough for balance cut, like why it's good. Okay. So the algorithm is defined, the problem is defined like this. Let's say that I give you like a where A is, let's say, is quite significantly small. Not just smaller than B, but like smaller than B by quite a bit. B is at least half, A is less than half by quite a bit. And what we're going to do is like, we have a graph, you have A, you have B. It will find some cut. This cut can be empty. Okay, return S. If it's returned, this is phi sparse. Maybe I draw it in more general way. This is S, phi sparse. And what's more is that everything, there's not, like it also return flow. And everything that is outside the cut need to be meshed to B. But this is not allowed. Like, I cannot mesh to this guy, for example. I only want to mesh to this. Okay. This is not just B, it's B minus S. And if you remember, like when we used MacFlow to solve this problem, it's indeed the case that everything after min cut, right? It will be meshed outside the cut. The flow here will not kind of reverse the cut. It just go to this one. And we need this. That is kind of important. Seems like a small thing, but actually it's important. So it meshed source and sink outside the cut. Okay. We're going to solve this in the same time. But for now, let's see why it's useful. Okay. We're going to use it to solve this balanced sparse cut or giant expanding set. Right? This is just a subroutine that if we have it and it's fast, then it's just the main subroutine for expanded decomposition, if you remember. Yep. what it does is like it like do this thing. It return a cut that is sparse, and it's either like a balanced cut, it's a balanced case, it's a balanced sparse cut, or otherwise it is not balanced. Like the cut here is like not so big, but then the complement is already expanding in G, not in G, not here, but just in G. Do you remember, like, it would be better if it's just expanding in this one, but we just get this in G. Do you remember, like, what's the subroutine that we use to fix this problem? What's the name?
The trimming?
Expanded trimming, yeah. Okay. Yeah, next class we're gonna solve both expanded trimming and cut and mesh using the same technique. And it's gonna be basically, it's like dynamic version of push Relabel. So it's a cool one. Yes, so you see. Yeah. Okay. So we kind of learn dynamic shortest path and push Relabel. And now like next class is gonna be dynamic push Relabel for solving this thing. Okay. For solving this cut and mesh. Okay. Right now I write this cut mesh. I mean cut and mesh. Okay. Okay, but for now, let's see why cut and mesh is useful for solving this problem. Okay. Well, like, I hope that you see kind of, actually, okay, let's just go with it. Yeah. This is kind of in your homework, basically. So what it does, like you will start with empty graph. You have active vertices, right? And you have many rounds for each round. Like you have log square round for each round in the cut matching game. The cut player choose A and B, just like before. And now we just do cut match. We do cut match on the graph of active vertices. Okay, so like this is, let's say in the beginning everything is active. We have A and B. Okay. And then it's gonna return some cut, maybe some cut, and some flow. Okay. And this is going to be sparse, right? And the idea is just, this is like a sparse cut, but this cut might not be balanced. So we kind of basically collect this sparse cut, and we look at the collection of our sparse cut. This Sj is going to be disjoint sparse cut. Okay? If the union of all this sparse cut so far is bigger than our balance threshold, then we are done. We get the union of sparse cut, which is sparse and balance. So we can just return the union and say that we are done. We get balanced sparse cut. Right? But if the union is not big yet, like this one, it's just the first cut, then what we do is just say that the guy inside here we want to delete. Si is the deleting set. We remove it from the active. It's not active anymore. And let M be the bipartite graph routed by the flow. So we get like, we extract the meshing. This is MI. Okay. And I want to draw it in a more general way. So okay. We're gonna delete this thing, right? And all this thing cannot go here. This is not possible. We don't want that. We just mesh here. Okay. And that's our meshing. This is our meshing. And we add it to X and continue. And just keep doing this. And then next round, we look at this graph. Like in the next round, right? This is quite important. We look at the new graph where we just work on this graph. We just work, like we just really remove it from your graph. And we compute cut mesh only in the active, like graph induced by active nodes. So that if you get a sparse cut, you get another sparse cut that is disjoint from the previous one. And continue. Okay, so this is important. Just so like you work on only active set, so that every disjoint cut, every sparse cut that you get are disjoint cut. Okay. So basically, what you're gonna get is like S1, and then maybe S2. They are disjoint; they don't overlap. And then S3, and S4, and so on. And each of these is sparse. And the union of them will be sparse. If they can overlap, then it's not the case. Why? Because, for example, if they overlap, maybe think like there are some really dense core, some part of the graph here. Maybe this is like something super dense. Okay. And something super dense here. And maybe, what? Okay. Maybe S1 is like this. S2, if it's like this, each of them is sparse individually, but the union of them might not be sparse anymore, because you see like kind of the cut size get charged to this guy again and again. So the union is not sparse. But if they are disjoint and each of them are sparse, then the union is sparse. Okay. So this kind of explains why the union is sparse. Okay. So if it returns this case, you're done. You're good. It's just balance and sparse. But if not, then what? Then you get that like you see like at the end you return this cut, which is not balanced but is still sparse. But we want to argue that the remaining active guy is expanding. Okay. Why is that? Well, the reason is just like we implement the meshing game, cut meshing game kind of with deletion perfectly. Like we want to argue that this cut mesh really simulate the valid meshing and delete player. Okay. And can you tell me like why is it important that F mesh sort and sync outside the cut? That is like, why is it the case that I need this thing?
If it's inside there, it's like deleted, and you do not want to match something to like delete.
Yeah, exactly. Like in the game, cut matching game with deletion, we can only match guys to the undeleted guy. Right? We can like this part is deleted. We don't want like in the game it works only when we don't match to the deleted guy. So we want to match to only undeleted guy. So that's the thing. Like, I mean, in fact, if we just use push relabel, like just what we learned right today, if we have A, if we have B, suppose that it's returned some cut S here. We know that all the excess is here because this is like S is like L at least K. So the excess which is like at level H, the dead guy is inside L, inside this cut S. The excess is already inside S. It means what? It means that everyone here have no excess. So everyone here actually send some flow. Successfully send flow. Today the algorithm today, everyone here actually successfully send flow to source, to sink. But the problem is just that if the cut looks like this guy might send flow to this guy. That's the problem. So what we learned today almost work. Okay? But it doesn't for this application, which is need to be stronger. So yeah. So next time we learn how to force all the flow to send to outside the cut. And the idea is to use dynamic push relabel. Okay. So yeah, any question? All right. Any of you do exam today? You, right? Okay. So, okay. Yeah. So next, we learn about this next week. Yeah. Right. Okay.